All right, so exam one is coming up. That's a week from today. Is that right? Is today the 20th? Yeah, okay. So I wanted to talk about that, of course, today. And also we have this Lab 3 to look at as well, or any questions that you have. Is there anyone that has a pressing question or any question that you want to bring up now? Just I want to keep in sync with where you're at. So, all right. So does it make sense to look at exam one practice problems today? Just talk about those a little. Okay. All right. Unless you'd rather look at the Lab 3. Do we need to look at Lab 3 today and wait till Wednesday to look at the exam? Who wants to do Lab 3 today? Who wants to do the exam today? There's kind of an even split there.
Yeah.
Huh?
Even split between the lab sections.
I got it. I'll do just a little bit on the exam, then go back to Lab 3, then go back to the exam again. All right. And mainly it's figuring these things out here. Give me well, these have answers, right? These sample questions, but these don't down here. Can someone give me pick one out that we want to look at, something that I haven't covered, that you're working on perhaps. Is anybody with a specific practice exam problem you've been working with? Now these things, you can't do this the night before, all right? It's not going to work. Because this is the sort of thing like you're learning how to play the violin. You know, you've got a concert, on Monday. So you're going to learn how to play it on Sunday night. That doesn't work, right? You got to practice kind of every day. And, you try a little bit, you get stuck, can't figure it out, you go to sleep, do other things. And then, a bell, a light goes off in your head. And then, oh, yeah, right, I got to count the loop differently. So you need to spend time with these problems. They've sort of developed a skill. It's a new skill set. You can't cram for this exam. Cramming does not work. Absolutely does not work. You've got to be very regular in your practice with these problems. So just get started. I would say, why don't we do it like this? Start working through these problems. And, and when you do them, the ones that have answers, don't look at the answer first, right? Really do your best to come up with the answer, then look at the answer. And then if you got it wrong, go back and try to figure out what you did wrong. And if you can't understand how to approach the problem, you're just totally lost. After putting an effort into it, then ask me about it in lecture on Wednesday. And then I will try to go into the details of how to approach that particular problem, or that class of problem. All right, so unless you have a very specific problem right now that you're grappling with, I'll move to Lab 3 then at this point. It's because if I present on this, it won't be as meaningful unless you first try to do the problems yourself. Right. And then when I present on it, then it'll become more useful to you. All right, let's go back and look at this lab. All right, which one of these are people looking at?
Exercise 1.
1?
Yeah.
All right, detecting prime numbers. Write a console program that asks the user to enter an integer greater than 1. Oh, wait a minute. Let's just do that. I'm not even going to read anything, but okay. Just going to do that. Ask the user to enter an integer greater than 1. Let's start with that. So I'm going to copy from Lab 2 something. I don't know, EX4, say. This is EX1, CPP. Enter an integer greater than 1. And then we'll have the integer. I'll call it n. I'm not sure whether that's it or not. All right. What is going on there? Enter an integer greater than 1. Oh, we didn't read it in. So CNN. Enter an integer greater than 1. 3. Okay, we got that working. Okay, now we don't have to think about that part of the problem, see? So that's good. We just got that detail out of the way. We got our development environment set up and practiced compiling and running. So now we don't have to think about that. The program determines if the number entered is prime and writes a message to standard output stream stating whether the number is prime or not. For example, if the user enters 42, the program displays 42 is not prime. If the user enters 47, the program displays 47 is prime. Develop 8 test cases that verify your program runs correctly for them. The test cases should contain some prime numbers as well as non-prime numbers. Include test cases that try to break your program so that you are sure you have implemented the code correctly. Include the 8 test cases within a multi-line comment near the top of your source code file. Make sure that the comment is nicely organized and easy to read and understand. All right, so let's do that. We'll start with the test cases. So we'll have, say, the user input, and then the result. And we're not going to worry about checking for valid user input. If the user types in an A, or a -3, we're not going to worry about that. It's not part of the problem. So 2 is the smallest possible number, and this is called a boundary case. When we talk about test code or test cases, you want to make sure you stress the program, and you want to check what's called the boundary cases. The smallest possible input, the largest possible input, anything that's funny or different. You want to try those. So 2 is prime. And then 3 is prime. 4 is the smallest non-prime. And then we would have something like 8, which is prime.
It's not.
Oh, sorry, not prime. Yes, not prime. And then maybe 9, which is not prime. And here's one that some time ago, like a lot of programs had a fault in the logic, and 27 was stated as prime according to their logic. So that's a good one to test. It's 3 cubed, right? That's 27. So it's, some people just look at multiples of 2. So we need 8 test cases. Let's use from the example the 42, that's prime, not prime, and 47. Do we get 8? 4. That's 8 right there, 8 test cases. I'm going to close the multi-line comment like that. So we'll try, after we write the code, we're going to use this to test it. So here we need to determine whether the entered value n is prime or not prime. So prime, to be prime, you can only be divisible by 1 and yourself. So what we're going to do is check all the numbers between 1 and n and see if we find a value that evenly divides into n.
Yes.
So what would we use, what construct that we've studied so far that you can think of that we need to use? Yeah, question. A loop, yeah, we got to use a loop. Check every number between 2 and n minus 1, including both of those. Doesn't that sound like a loop? You got to do something n minus 1 times or n minus 1, whatever. So we can use a while loop or a for loop. So for loops are more compact, and they're easy if you know they're appropriate if you know the exact sequence of values that you want to look at, which is our case. A while loop is more general. It's useful for more complicated loop conditions. So let's use a for loop. We'll start at 2. And we don't want to hit n, so we'll go less than n. And we're going to look at every value. There's other ways to check it. You don't have to check every number. I think you can go to the square root of n. Does that make sense? Square root of n. We can do that, actually. I'll call that the square root of n. I think that's it right there. I think we need the CMath. Maybe not on this computer, but on the lab machines. I think you need CMath for that. That worked. Oh, it's not going to do anything. It's going to just.
Do you want plus plus I?
Well, it'll finish, huh?
Do you want plus plus I or I plus plus?
Plus plus I or I plus plus doesn't matter because this here is. This is like a whole statement unto itself. So, we're using I. We're not really using I here. We're just incrementing I. So plus plus I or I plus plus doesn't matter in this case. If it was part of this expression here, then it would matter. If it had something like that. If it was part of a larger expression. But see, this, you can think of this section right in here, this is the end of loop operation, and it stands alone as its own kind of statement. So I is not being read or used by anything else in this point. So it stands alone. A lot of people like I plus plus, but actually plus plus I is, I think it's more efficient. So I use plus plus I. Maybe it's not more efficient. I don't know the internal details. All right, so if I evenly divides what? N. Then it's not prime. Say it and we're done. So I'm just going to rough it out like that, see? If n even, how do we express that with the tools that we have, what we know? That if I evenly divides n, how do we do that? You need to know this, for the exam.
N mod I is 0.
Exactly. N mod I if n mod I is 0, that means when you divide n by I, you don't get a remainder, right? So this is a remainder operator. N mod I means divide n by I, throw away the result except keep the remainder. So 3 mod 2 is 1, because you can take 1, 2 out of 3 and you're left with the remainder of 1. So if you get 0 as a remainder, that means I evenly divides n. That means it's prime. And so we can, right on that spot, right there, we know that it's not prime. And maybe I'll write a little bit more there. I'll put the n in there. N is not prime. And we want to finish here, so we can break from the loop. I'm not going to break from the loop. I'm just going to return. I'm going to return from main. There's nothing else for us to do there. I'm going to get rid of that comment, because I can, when I read this, I know what that is. Clean this up here. Now, if we finish the loop, if we never hit this return, that means we went through the loop and we never found no I evenly divided into n, right? No I. There's no such number that evenly divides into n, so we know that n is prime. So we'll print out n is prime. Oh. Main is non-void. We'll have to return a 0. See, this int up here, this means that the function needs to return a value. Oh, we didn't talk about return yet, did we?
No.
So returning here, it's the same thing as hitting the last line of code and going beyond the end. It's like, I'm finished. So we're telling the program, or we're telling the execution environment here that we're finished. And we'll talk more about this when we get to the chapter on functions, which is like coming up really soon. Is that right? Functions are coming up. Yeah, the next lab 4. So let's see if this works. Let's try the test cases. 2 is prime. 3 is prime. 4 is prime. What do we do wrong? We got it wrong. Huh?
It started with I equals 2 and said that I has to be less than the square root. Square root of 4 would be 2.
The square root of 4 is 2. Oh, we want to hit the square root. Oh my gosh. Yeah, I never used this before. And by the way, if you do it like this, it's okay with me. It takes longer to finish, but that's how I've always presented it before, because I'm focused more on you grasping the logic, the looping. But this is obviously a way to make it run better. faster. So we want to be less than or equal to the square root. Test. See, I'm going to do all the test cases again, just in case something went wrong there. 4 is not prime. We got it. Oh, that's great. The next one was 8. 8 is not prime. Then the next one was 9. 9 is not prime. Then the next one was 27. Not prime. That works. And then we did 42. Not prime. And then 47. Prime. So the test cases pass. There they are. That's done. I'm going to show you a different way of doing this. And this will be where I'm not using the return statement. And this will be useful when you do the other problems, actually. Because you won't be able to do it like this with one of the other problems in this lab. We'll use a Boolean variable. Is prime. So we'll assume that it's prime. So we have this Boolean variable, that's a variable. Is prime is a variable. It's one of two states. It's either true or false. We'll start with it being true. So we're going to assume n is prime. And then what we're going to do is in this loop is search for a place in here, in this loop, we're searching for an I that evenly divides n. When we find it, we say, oh, our assumption that n is prime is false. And so we have to change our minds. And instead of returning 0 here, we're going to set the is prime variable to false. So here we're using a Boolean variable. So when we leave the loop, we test if is prime is true, then we print that, n is prime. Else, n is not prime. Now we avoided the return statement. Let's see if that works. $27. 27 is not prime. You see the difference there? So we have a Boolean variable. See, we can't do it the other way. We can't do it this way. We can't say it's false and say, look for a place to set it to true. We can't go in that direction. Because for us to set it to true, we need to know that all I doesn't divide into n. But to go in the other direction, to start with is prime true, now to change the state and change is prime to false, all we have to do is find one I instead of saying, and then once we find that one I, then we can change the state. So that's the key. You can only go in that direction. You can't start with the other assumption that is prime is false. You can't work the logic out, because I don't know how to do it. So in these kind of problems, you have to sort of think about both possible starting points. When you use a Boolean variable, should I start it at true and then set it to false later? Or should I start it as false and then set it to true later? And usually you have to pick one and not the other. And one way doesn't work. And this is a case where we can't set is prime to false. Well, we can't work the logic out. We have to start with true. All right. One other thing, the loop here, look, once we know that we found one I that evenly divides n, we don't have to look at the rest of them. So, but we're continuing, right now we're continuing with the loop. We keep looking at all the others. But we don't need to. We could break the loop here. Does anybody know how to break the loop? How do we break the loop right here? How do we break the loop? That's a hint. See? I use that about 5 times. Break. That's how you break the loop. And yeah, let's see if that works. That's good. So this just, although it's, once again, it doesn't really matter, but I mean, it makes the program run faster, although we can't tell the difference. All right. That's exercise 1. What about exercise 2? Listing prime numbers. Write a console program that reads a positive integer entered by the user, just like we did. The program computes and displays all the prime numbers between 2 and the number entered. Actually, the number entered needs to be bigger than 2, or 2. So the user's going to enter in a number like 8, right? And then it displays all the prime numbers between 2 and 8. So it'll display 2, 3, 5, 7. So that's what it will print. Now to solve the problem, you need to nest an inner loop within an outer loop. Develop test cases and include them in a multi-line comment. All right. So I'll make a copy, CP, that's the copy command. You need to know that for the exam, as well as the other commands, ls, mkdir, and so on. And then let's edit. Let's edit this. Now the test cases, it didn't ask for 8, but we can do this. If we enter in a 2, it should just print 2. If we enter in a 3, it should print 2 and 3. Enter in a 4, should be 2 and 3, the same thing. 8, 2, 3, 5, 7. 9, 2, 3, 5, 7, same thing. 27, 2, 3, 5, 7. I don't know if I want to do this. That's it?
Yeah.
And that's as far as I want to go. I get it? Right. So here's our test code. Enter an integer greater than 1. Let's just keep it like that. Now what are we going to do? This thing determines whether n is prime, right? So we have a loop that determines whether n is prime. I'm going to change this around. Instead of n up here, watch this. I want to make that a k. Enter an integer greater than 1. And I'm going to replace that with a k here, see? So we're going to read in the value as k. K is the number. Now this code down here is already written to decide whether, n is prime or not. So we're going to have a loop that goes from 2 to k. And for each of the numbers between 2 and k, we can decide whether one of those numbers is prime or not, right? it's hard for me to explain this. Oh, by the way, this is square root. That's square root of n. Yeah, that's right. So this is the code right here. This is code to determine if n is prime right here. And this is stuff, you know, if n turns out to be prime, right, then we're going to print n. And if n is not prime, we're not going to print anything. We just want to print n when n is prime. So we have a block of code already that gets an n, and if n is prime, it prints n. That's what we want to do, right? So we're going to look at, like for 4 here, we're going to start at 2. Is 2 prime? Yes, print 2. And then we're going to go to 3. Is 3 prime? Yes, okay, print 3. Then we're going to go to 4. Is 4 prime? No. Oh, don't print anything. And then we're done. So we need to have an outer loop controlling that thing. The outer loop is going to produce different values for n. We're going to start with n equaling k, and we're going to look at k plus 1 and so on. And then we bring n all the way up to k itself. And for each of those values that we assign to n, we're going to determine if that value n is prime or not. If it is, we'll print n. If it's not, we won't print anything. So we need this loop on the outside that's going to do that. So for integer n equals 2, n less than or equal to k, plus n. See, that's the controlling loop right there. You see that? We're just embedding everything. This is the code. We already wrote that code.
Should that be a semicolon after K in the for loop?
Yeah, that's a semicolon. Thank you. Saves us some time. Just going to clean this a little. Now notice this whole thing is now embedded in this outer loop. So we need to show that all that block of code is included in this outer loop. So we're going to use an indent, an extra indent to show that relationship. And we're done. I want to get rid of that space. Who thinks that's going to work? Let's see, I feel 98% positive. Let's see. It compiles, that's a good sign. All right, let's test, which test case do we want to use? How about 27? We're going to go for broke. Look at that. One little adjustment. I want the prompt to go to the next line. So when we're done this loop, they'll just go to the next line. And I'm sure it works for the other ones, right? It works for 27. I'm sure it's going to work for the others. Except the boundary case, we should always test that one. Okay. See how we work that one out? So this is called a nested loop. This is the outer loop, which is controlling n. And this is the inner loop, which is controlling I. And so we got these variables. We got k, which is the integer uses k and it never changes. Then n is controlled in the outer loop, and n moves very slowly. And for every new value of n, I ranges from 2 to the square root of n. That's what we do, square root of n. So I moves a lot. You can think of I as like the second hand on the clock. N is like the minute hand. K is like the hour hand. All right, that's that one. What about factoring numbers? Did anyone get this? Or generating random colors. Did anyone get that? Is this due? When is this due, by the way?
Friday.
This coming Friday.
Yeah.
I'm just showing you all the answers. I'm not going to do this all the time, right? Because I showed you what that worked, exercise 1 and 2. So what your approach should be is maybe you took it down in the notes, took a picture of it, whatever. I'm going to post it on the internet, on the YouTube. But try to recreate the thinking, if you can, on your own without looking at your notes. Try to reconstruct that creative process where you come to the solution on your own. And I know it's hard in the beginning. That's why I'm showing it to you. And if you just say, I don't got time for that, I'm just going to submit what I saw there, then you'll get credit for the lab, but you won't have developed that skill, right? Yeah.
I tried exercise 1 and I did almost the exact same thing we did in here, except I didn't use square root. I just divided by all of the ends.
Yeah, that's good.
But I kept getting a floating point exception, and I don't know why.
Oh, I'll take a look at that maybe in lab. Yeah. All right, factoring numbers. Factoring numbers is a tough one. Or generating random colors. Did you look at these? These two, 3 and 4.
One defeated me, so I spent like 3 hours trying to figure out.
Which one were you struggling with?
The floating point exception.
Oh, that one. Oh, so you didn't even get to this one yet. What should I do? Should I do 3 and 4 or one of them, and then, or should we go to the exam problems and talk about those? What do you want to do? You tell me what to do. Who wants to do exercise 3 or 4? Who wants to start looking at the exam problems? That's like such an even split, really. All right, let's go and do the exam. Now we still have time. No, it's good to struggle with these. So I'm going to leave these alone, maybe, so you can tackle those in lab. And let's go and look at the exam problems. So let's do exam 1 practice. All right, let's take a look at this. Now, these are all problems from previous years. That's just coming on Monday. All right, let's take a look at this one. How do we understand this? Here's a block of code. When the code in figure 1 runs, what does it output to the console? All right. Let's try to understand this one. When this code runs, what does it output to the console right here? Well, we only have one variable, I. That's problem 1. So what you can do when you analyze this problem, sometimes it doesn't always work, but sometimes you can just keep a record of what the variables equal. Now you're going to start, you can approach this in 2 different ways. One is you kind of look at the whole thing and try to understand what it does. That's what everyone wants to do. And the other way is we're going to simulate the computer. We're going to execute it line by line, just like the computer, in slow mode using our human brains. Now, if the loop is really long, like the loop gets large, it has to repeat 100 times or so, and we can't do it then we have to do some meta reasoning. And we can't simply execute the code as if we were the computer. We have to sort of reason about it and say, well, you know, it does this thing a million times, and so therefore, dot, 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 you come to some conclusion. And this problem, however, is not that case. This problem here, I can see it and glancing at it. Well, I made the problem up. That the loop isn't going to run very much. Because look at I here. See, the loop condition is I is less than 66. I starts at 6. And we're not adding 1 to I. We're multiplying I by 6. So once, you know, if we start at 6, and then we multiply by 6, we're going to get 36. And then after 36, we're going to multiply by 6 again. We're going to get something big, more than 100. Certainly bigger than 66. So I can see that the loop is going to iterate twice. You know, when I glance at it, so I wrote the problem. So let's do it. I is 6. Oh, what does it print? It says, what does it output to the console? Okay, that's the problem. So we start executing. So we pretend that we're the computer. We're simulating the computer. Usually computers simulate humans, but now we're humans simulating the computer. So I is created and assigned to 6. That's the first statement. How many statements are there in this? How many top-level statements are in this snippet of code? Two. Very good. Excellent. So we have completed the first statement. Now we're going to complete the second statement. So this is a while loop. This is the loop condition. When the loop condition is true, we do the substatements. And we check the loop condition. If it's true, do the substatements. So right now, when we start executing this second statement, the while loop, the loop condition is true because I is 6. 6 is less than 66. So we're going to output I minus 6. That's 0, right? So what do we do with the 0 here? I minus 6 is an expression. It computes to 0. Are we modifying I?
No.
We're assigning 0 to I? No, we're using I. We're not modifying I. What do we do with the 0? Well, yeah, we print it. It becomes the left-hand side of this output operation. I mean the right-hand side of the output operation. So print the 0. And then we print a blank. That's just so we get neat output. Now the key here, and this is what some students will make a mistake, is that they set I to 0. They get confused at this point. They think that, oh, we just computed a 0, and now I is 0. So that's why I'm spending time on this. I don't want anybody to make that mistake. All right, now we go to the next statement. I is what? Well, we got it up here. I is 6. We didn't modify I. So I is assigned to 6 times I. So 6 times I is 36. I becomes 36. I'm sorry. I becomes 36. Sorry, that's not right. I becomes 36. Now we're at the bottom of the loop. So we evaluate the loop condition. 36 is less than 66. The loop condition is true. So let's execute the substatements. We're going to print 36 minus 6. So 30. What's I?
36.
36. It's not 30. Okay. And now, then we print that space too. Right? Remember, the first thing we do is left to right evaluation. The first thing we do is that. Of course, to do that, we have to do this first. So the subtraction operation is the operator with the highest precedence in this statement. This is done first. Then these two, they tie on precedence because it's the same operation, right? but we do left to right evaluation. So that means we do the leftmost output operation first. So then we, the value is then sent into cout. And then this thing that I have highlighted evaluates to cout itself. And that's a convention that's used frequently in programming APIs because you can chain these operations. So if this expression didn't evaluate to the left-hand side, cout, then we wouldn't be able to chain it like this. So that gives us this chaining ability. All right, so now I is 6 times 36 is assigned to I. That's a big number, right? It's bigger than 66. So we don't have to waste time on that. It's just a big number. So that when we evaluate the loop condition, we know the loop condition is now false. So we don't do the substatements, which means we don't print anything more. So we're done. So that's how to do that problem. Let's see if we got it right. Looks good. All right, let's go to the next one. Suppose that t is an integer variable, write code that prints cold when t is less than or equal to 50 and hot when t is greater than 50. So I'm going to show you, well, actually, it's just the answers right here. I'm not even going to write it out. If t is less than or equal to 50, print cold, else print hot. Now, I wrote this question before I changed my style in this class. So I would do this now like this. If t is less than or equal to 50, then cout cold, else cout hot. So these are two different styles. Look here, this is 5 lines. And this is 8 lines. So this fits more easily on an exam paper. That's one benefit of using this other style. But both of these are good if you like either of these. This one here is more common, by the way. This is the more typical style in a C++ program. What about this one? Now here's an example where we can simulate the computer. This one here, 3. Let's read what it says. When the code in figure 2 runs, what does it print? So what does this code print? So we're doing exercise 3. This is an example of sample code that we have to reason about. We can't simulate it completely. We can't simulate what the computer does completely because it's too much work. The loop is going to run for too long. So how do we reason about this one? Well, let's pick out a few important facts first, just as to guide us to the answer. Look at where does it output anything at all. Look at this here. We had an output operation inside the loop. So we repeated this output. But look here, the output operation is outside the loop. It's the 4th statement in the code. This is the first statement. This is the second statement. The for loop is the 3rd statement, and this output operation is the 4th statement. So we're only going to print one number.
Mm-hmm.
All right. So the problem is to figure out what n is. And the first two statements are really simple. There's a k, there's an n. K is 2, 2, 2, and n is minus 4. Oh, that's easy. That's it. Like, let's make a note of that. K is 2, 2, 2, and n is minus 4. I'm just going to make a note so we don't. Oh, and when I make that note, by the way, I'm starting that simulation process. I'm saying, all right, let me execute line 1, create a k, assign 2, 2, 2 to it. Now execute line 2, create an n, assign minus 4 to it. All right, now execute line 3. So I'm starting the simulation process in my mind. But I know, because I glanced at it already and I made a problem, I know that the loop takes too much time, and so we're going to have to make a jump using reasoning and figure out what n is going to be. But nevertheless, I'm going to start, just so that I can understand the code, I'm going to start in my mind simulating how it executes in the computer. I'm going to do one statement after another. I'm going to keep a record of the variables. There's a k and there's an n. K is 2, 2, 2, n is minus 4. And there's also an I. But this is what the state of this computer simulation is after the second statement finishes executing. Now let's execute the third statement, and that's the complicated one. So the third statement is a complex statement, and there's a number of steps involved that we can go through. The first step is to create an I and initialize it to 0. That's the for loop initialization section. Now, in the for loop, it's just like the while loop. This would be like the statement that comes before you see the while loop. This is the loop condition in the middle. And this is the thing that would be at the bottom of the while loop. It's the end of loop operation. So the loop condition needs to be evaluated. So we don't have to worry about this plus plus I. We don't have to think about it until we hit the bottom of the loop. So after initialization, then we check the loop condition. If it's true, we'll do the substatements, and then we'll do the end of loop operation. If the loop condition is false, we don't do the substatements, and we don't do the end of loop operation either. So the loop condition is that I is less than k. 0 is less than 2, 2, 2. That's right. So the loop condition is true. So what do? Do we increment I, or do we do the substatements? Substatements, good. Increment I at the bottom of the loop. You just have to nail it in there. Just repeat it to yourself a couple of times, many times until you got it memorized. It's hard to look at this whole thing and just see, you've got to kind of figure out the pieces. All right, so what does the body of the loop do here? What do the substatements do? It just adds 2 to n. So now n turns into, I'll do it like this. What was that? Minus 2, right? Yeah. We add 2 to n, so 2 is now minus 2. I'm going to keep track of these values with this dot dot here. Now we finish the substatement, so we do the end of loop operation, which is to increment n. Oh, sorry, increment I, thank you. After we do the end of loop operation, what do?
If it can check the condition.
The condition, the loop condition, is I less than k. It's true. So then we're going to add 2 to n. So now n is 0. We're at the bottom of the loop. Do the end of loop operation. All right, so do you see what's happening here? This I is heading to hit k. What happens when it hits 2, 2, 1?
Everyone's a final time.
It does the substatements, right? Huh?
It's the last time the loop runs.
Exactly. It's the last time the substatements run. Because when it hits 2, 2, 2, I is no longer strictly less than k. So these states of I, there's how many times does the substatements run?
222.
222, because we started at 0, right? So we added 222 times to n. We added 222 twos.
Yes.
So how much did we add to n? 444. So we added 444 to n. But we started at minus 4. So we hit 440. So, and then we exit the loop and we print n. So we're going to print 440. Everyone get that? That's not too bad. Yeah. All right. To me, I think that's the hardest problem on the exam. That one. These type of problems. Not going to be exactly this problem, but it'll be just like this. Okay? I think these are the hardest. The ones where you have to reason about the loop, and you can't. Your simulation can't. You can't just simulate the code and figure out what the number is. All right. Oh, let's check our answer. 440. What about the next one? When the code in figure 3 runs, what does it output to the console? Well, here we have this, the post increment and the pre-increment and this modulo operation. Those are the tricky things, right? The things that you're probably learning. And so what does it output to the console? And look, it's the last line when it outputs something at all. So it's going to output one number. This right-hand side will be evaluated to a value. And we're going to send that to this standard output stream, cout. We're going to print one number. What is that number? 1? Did you get that by hitting show answer, or did you think?
I went through all these.
Just kidding. So, all right. So, how do we think it through here? Let's think it through. All right. So there's an n. We're going to initialize it to 9. Now the first statement is finished. So this is a case where you just simulate the computer running. We don't have to reason about the code. We just have to remember how the computer executes these operations, the order in which they run. So the first statement is to create an n and assign 9 to it. And the second statement is to create a k and assign the result of that expression to k. Okay? So let's make a note. What's k going to be? Well, we have 3 operations. There's multiplication, there's post increment, and there's addition. Huh? So we do the addition first, right? So 1 plus n, ignore the plus plus, right? We have to do that later. It comes after the n. What's that? I'm sorry. It was this chair squeaking. I thought someone said something. So it's 1 plus n, which is 10. 1 plus n is 10. And we can either increment the n now or wait until everything is all over. It doesn't matter. And I'm not sure how the compiler does it. After you add 1 to n, does n get incremented now? Or does it get incremented later? Can't remember.
You just test it by putting 2 times on right there.
Yeah, I've done that before, and I don't want to do it. So we could do n plus 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 n plus plus like that. Yeah, I don't want to get into that. You don't usually see that. I've never seen it in practice ever. So let's leave n alone for now. So 1 plus n is 10 times 2 is 20. So k is assigned 20. Did I get that right? Okay. And now let's increment n before we go on. So n is now 10. Now in the next line, we have to do the plus k first. That's the pre-increment. So k becomes 21. I should have done it like this. K becomes 21. And then we add n to k. So we're adding 10 to 21. So that's 31. So 31 mod 3. What is 31 mod 3? Well, that's an easy one, right? 10 threes. There's one left over. We got it. And the answer is 1. There it is. Which one should we do next? Because we're running out of time. Let's pick the one that, because you've looked at them already. It's one.
5, just the exclamation zero equal thing. I wasn't totally familiar.
This one here?
No, the one that's underneath it. Sorry, figure 5.
Oh, figure 5, problem 6. Let's do that one. Problem 6. We're going to omit 5. When the code in figure 5 runs, what does it output to the console? And this is, we don't have to reason about it, we just have to execute it. So we have an x, we assign 1 to x. We've got a y, we create a y, assign 2 to y. And then if this condition is true, then we're going to print non-zero. If this condition is false, we're going to print 0. Yeah.
What is the exclamation mark doing again?
Oh, this means not equal to. This is a not equal to comparison operator. This does a comparison. Is the left-hand side not equal to the right-hand side? If that's true, then this evaluates the true. This is a Boolean expression. It's either true or false. So this is the left-hand side. Whatever that is, we're going to compare it to the right-hand side, 0. So is the left-hand side 0 or not 0?
Not 0 because they're double 1.
Not 0 because what?
Double 1.
Why is it double?
Because it's floating point division, right? Because the y is this y is declared as double. See that? That means the y is a floating point value. So the compiler is going to say, oh, you have a floating point value in this division, and so the division is not integer division. The division is going to be floating point division. So you're going to retain the fractional component. So x divided by y is 1 divided by 2, floating with floating division. So we're going to get 0.5. 0.5 is not equal to 0. So that's true. So we're going to print non-zero. Non-zero. Any questions on that one? That's it then, right? I think that's it for today.